A screencast for the homework solutions for chapter 12. What I've noticed is that we have not had as much time to really go into depth discussing this chapter, which is a challenging chapter. So I'd like, I did do, I think, an ed puzzle, talked about some of these things, but I think it is challenging. So I'd really encourage you, if you struggled with this homework, first of all, to work with other people, talk with each other, like spend time outside of class, not being isolated, but really trying to think about it. And then when I'm going over this, if you still have questions, to please ask me. So my goal is to be done with new content before spring break, but that doesn't mean we can't go back and revisit things. And I think this is a topic we may need to do that with. So I really hope you put in good effort on this. Problem 13 here. We have four spheres, each with a mass at different locations, and it's asking, first of all, what's the center of mass of the system? So the summation of the masses times the positions in each x and y direction divided by the mass would give us that location. So here I've got these two masses are both at 10 centimeters in the positive direction on the x-axis, but the total mass of the system is 700 grams. So that comes up to 5.71 centimeters. These two masses are 8 centimeters above the x-axis in the positive y direction. So that gets me that summation in the top divided by 700 grams gives me that position. So that is the overall position of the center of mass. It's along this diagonal line. So in this case then, to find the total moment of inertia, if we had something sticking into the page here through A, and this whole system was rotating about A, we would look at each of these individual A, B, C, and D spheres as a point source at a certain distance away from this. And we would add the sum of those moments of inertia. So B was 0.2 kilograms at 8 centimeters away. D was 0.2 kilograms at 10 centimeters away. And C was 0.2 kilograms at this distance away, which I had to figure out, which was 0.128. The summation of all those gives me 0.656 kilogram meters squared as the moment of inertia. I don't know why that 6 looks weird there. At any rate, here this is asking you to find the net torque. Well, this force is pulled perpendicularly at the radius, so it says 4 centimeters diameter, so I'm going to convert to standard units and convert to radius. So that is 0.6 newton meters of clockwise torque. This would cause 0.4 newton meters of counterclockwise torque. The net torque would be 0.2 newton meters counterclockwise. No. That's clockwise torque, and so that is negative. I need to fix that. It is not bold. And I'm going to put that as a negative sign. And then the background color is going to be light gray. So you'll never know that I screwed up. Nice. And then I'll also end up doing something like this where I get a new one where it's like, hey. Clockwise. There. Thank God nobody knows that I screw up like that. I don't know why I thought that was different, but clockwise torque would be negative. For P24, there's a number of ways to do this. This is a torque versus time graph. The linear analog is force versus time, and the area of a force versus time graph gives us impulse, which is Ft. So this would be T, torque times time. Talk about that down there. The other thing is, if I think about this as angular acceleration is torque divided by moment of inertia, and it gave me the moment of inertia, I could make an angular acceleration versus time graph. And therefore, the area of an acceleration versus time graph gives you the total change in velocity, just like the area of a velocity versus time graph gives you the total change in position. So in this case, my total change of velocity is 0.5 rad per second. This also, again, the area of this, the impulse divided by the moment of inertia, would give you the same answer. For problem 31, this is a really good one to think about being able to do. I don't know why my page is a little crooked here. So you've got an object here, a cat, I think it's a food dish here, a cat here, and another cat over on the left side of this fulcrum, and you want to know where this second cat should be that it would balance. So 5 kilogram cat, 2 kilogram dish of food. Big ideas: torque is equal to perpendicular force multiplied by d, or r, the distance from the fulcrum. Counterclockwise torque equals clockwise torque for a system in rotational equilibrium. So in this case, I've got 2 times 2 meters times g, that's over here, plus 4 kilograms times, we don't know what distance, times g, causing this torque over here. That would equal to the 5 kilogram cat 2 meters away times g, which would be the clockwise torque. So I have one unknown. When I solve for that, that gets me 1.5 meters. Remember, that measurement is always from the fulcrum, so that cat would be 1.5 meters to the left of the fulcrum, so pretty close to the food dish. For P32, so you had a 60 centimeter diameter wheel on a car. The car was going 20 meters per second. So again, convert that to 0.3 meter radius, and the angular velocity is equal to linear velocity divided by radius. So that tells me the angular velocity of the tire. And if I want that in RPM, well, if I have radians per second, there's 60 seconds in a minute, and there's 2 pi radians in 1 revolution. So you get revolutions over minutes. That's the conversion that I do. It came out to like 638, I think. So when you have an object rolling, the thing that's neat is at the bottom, where a wheel or tire is touching the surface, that the speed is actually 0. It is in contact with the surface. So it is moving 0 meters per second. Well, the average speed of the tire being 20 meters per second means that the top part would actually have to be moving forward twice that speed, or 40 meters per second. So that's a really interesting thing that was mentioned in the chapter. Problem 45 was asking you to find the angular momentum of this 500 gram rod. So angular momentum is I omega. So angular or moment of inertia for a rod is 1/12 ml squared. It gave you the mass is 0.5 kilograms, gave you the whole length is 2 meters. So that gives me the moment of inertia. I'm going to convert revolutions per minute. So that's 120 per minute, which is 120 over 60 seconds. So that's 2 per second, multiplied by 2 pi radians for every 1 revolution. And that gets me my angular speed. So overall, multiplying those two together, you get around 2.1 kilogram meters squared per second as my angular momentum. For 62, I wish I'd drawn this a little bit bigger. That's good. Oh, that's too big. This is a really good type of problem, and I would like to make sure you understand how to solve it. So the key here is we've got this plank attached to a wall. It's got a mass. And if it's a uniform plank, that'll act at center of mass, so that's 3 meters. This is attached to the end, that's 6 meters. And this person is sitting 2 meters to the left of where the rope is attached, and they have a mass of 80 kilograms. So they are at 2 meters from this point, 4 meters from the left point. Because this plank is attached to the wall, and we don't know whether the wall is pushing or pulling on the plank or acting up or down on the plank, we have a lot of unknowns. So by placing the pivot point or fulcrum at that location, those unknown forces act at 0 distance, which means they will not affect the torque. You can choose where you want to place a pivot point, and for an object that really is in rotational equilibrium, the torques will always balance out. But if you place it at a location where you've got an unknown force or unknown forces, that basically means that that's an unknown you can get rid of, because an unknown times 0 distance gives us 0 torque. So I hope that kind of makes sense. So once again, we're going to look at torque counterclockwise, or equals torque clockwise. I think I have the clockwise part over here. So clockwise, mass of the beam, g, distance of the center of mass acts from the pivot point, which is 3 meters, plus the mass of the person, g, the distance the person is acting from the pivot point, which is 4 meters. And the only thing causing a counterclockwise torque is the tension in this rope. Well, we need to find the perpendicular component of that. That would be t sine 30 degrees. And it's acting 6 meters from the fulcrum. So essentially I get all these Newton meters of clockwise torque. 3 times tension meters represents the counterclockwise torque. So I'm going to divide the distance out. I end up getting 15,255 newtons. That means that the person resting here should be worried if this is only rated for a tension of 15,000 newtons. Moving along here for problem 69, I solved this actually 3 different ways, so I hope you look at that. If I need to find the time that it's going to take this to hit the ground, I need to find its linear acceleration. Well, if I have 4 kilograms here, 2 kilograms here, obviously this will accelerate downward. But its rate of acceleration depends not only on the net force of the system, but also the equivalent mass, meaning gravity is pulling this down, but gravity would be pulling this down. And also, this circular disk has a moment of inertia, which opposes its change in motion, or its acceleration as well. So it gave us this as the diameter of 12 centimeters, so that becomes 0.06 meters radius. It says that this has a mass of 2 kilograms. So the friction exerts a torque, 0.5 newton meters. How long does it take this thing to reach the floor? So if I think of this just as a force problem, Newton's second law, F net over m equivalent, this would cause mg down this way, subtract off the mg caused by this, and then subtract off the force of friction. The equivalent mass is 4 plus 2, and if this is a solid disk, which has a coefficient of 0.5, because we can figure out that the moment of inertia for a solid disk is 0.5 mr squared, then I can say that this acts as if it has 1 kilogram of mass. So when I do that, I'm left not knowing this. To find the force of friction, we can think of, although the friction acts at this axle, it can create an equivalent torque of 0.5 newton meters. Well, if the force of friction was acting at the edge over here, it would act like a 8.33 newton force. In other words, 0.5 newton meters of torque is equal to 8.33 newtons of force acting at this 0.06 meter distance. So since these other two forces are acting at the outside radius, I wanted to think of friction acting there as well, just for comparison purposes. So that means torque force equivalent caused by the 4 kilogram mass minus force equivalent caused by the 2 kilogram mass minus force equivalent caused by friction, all that over the equivalent mass of the system gives me that acceleration. It's got to fall 1 meter, and I can solve for the time, 1.11 seconds. There are a couple other ways you could do this also. So method 1 was forces, method 2 is torques. Get the clockwise torque down here, counterclockwise torque up here. So counterclockwise torque is caused by the 4 kilogram mass. Clockwise torque would be caused both by the 2 kilogram mass and friction, since it would oppose this thing's motion counterclockwise. So I added those two torques up, got my clockwise torque, and so my net torque was counterclockwise by that amount. That's simply taking counterclockwise torque minus clockwise torque. So now, if I know my net torque and my radius, I can figure out my equivalent force of the whole system. That's 11.27 newtons divided by the equivalent mass of the system. That gives me the same acceleration I had before, 1.61, and the same time. Finally, down here, we're going to use the net torque and moment of inertia. We could get the angular acceleration and then convert that to linear acceleration. So the net torque is something I figured out up here, 0.676 newton meters clockwise. Moment of inertia, well, that's the pulley, and then the two masses, act as if they are at the edge of the disk, so they're point sources essentially at that outer edge, and that would just be mr squared. So I've got that amount of moment of inertia for the 4 kilogram mass, this amount of moment of inertia for the 2 kilogram mass, and then this, again, is the moment of inertia of the pulley. 1/2 complete mass of the pulley, 0.06 meters is the radius squared. So that gets me the total moment of inertia. I already knew my net torque from method 2. Get an angular acceleration. Angular acceleration and linear acceleration relate to each other like this. So once again, I get the same linear acceleration of 1.61 meters per second squared. We don't want that. And we get the same time. All right, this is number 74, which is the last one. This is a parallel axis theorem problem. I tried to draw it as best I could, but you know me in drawings. At any rate, what you've got here is you've got something, and again, they give you, that's a fantastic 60 centimeters in diameter. I changed it to standard units and make it radius. So this is a 0.3 millimeter radius solid disc, and it's attached on the end to an axle. And basically, it is then going to fall down below the axle. So it's rotating about a pivot point here, even though the center of mass is here. So to find the angular acceleration initially, the torque is caused by the gravitational force downward on the center of mass. So essentially we could think about that like this, except I didn't draw it very well. So that is the force. It's acting at this distance, 0.3 meters away from the axle, and it's going to cause this thing to rotate clockwise and fall down. Now, as it goes lower and lower, that effective distance away from the axle will decrease to the point where when the center of mass is directly beneath the axle, there will be no torque any longer. That gets to the concept of what the heck a lever arm is, which is the effective length. There are other ways you could figure that out as well. So at any rate, I'm going to use Newton's second law for rotation, net torque over moment of inertia, similar in concept to force over mass. So that torque is mg multiplied by the distance away from the pivot point. So that's mg times 0.3 meters. The moment of inertia is the moment of inertia of the disk plus the extra moment of inertia caused by being rotated somewhere other than its center of mass. So this would be 0.5 mr squared. This is md squared, where d is the distance from the center of mass to the point of rotation. Now here, r and d happen to be the same value, 0.3 meters. But if the axle was located somewhere other than the very edge, like 2/3 the way out, this would stay the same. This distance would not stay the same. So we get 14.7 Newton meters of torque divided by 0.675 kilogram meters per second squared, and we get an angular velocity or acceleration of around 22 radians per second squared. Now this is asking for the speed at the bottom. Remind me, because you need to remind me, that we need to go over the race, the rolling race, where you have a solid disc, a hoop, and a solid sphere rolling down a hill. And we can use conservation of energy to figure that out. But the energy at the bottom of the hill is both linear kinetic energy and rotational kinetic energy for those objects that are rolling. It's only linear kinetic energy for something that's sliding, which is why it always tends to win or beat out objects that are rolling as well. So with this, it's a little different because we do not think of this as having linear kinetic energy. Since this object is just rotating around this axle, and at the bottom of the height, we don't have a linear kinetic energy anymore because parts of it aren't moving at all. Then we're only going to think of this as rotational kinetic energy. mgh equals 1/2 I omega squared. We know all these things except omega, and we can find that as about 6.6 radians per second. So hopefully that helps out. If you have questions on these, again, don't hesitate to ask in class, because I really think we've skipped over this a little more than we should as a chapter, even though we spent some time on it. This is a challenging topic. It always will be. Thanks, and have a great rest of your day.